Hello, everybody. Good morning if it's your morning. Happy Friday, even if it's not. Sorry for starting this session a little bit late. We're having some technical issues, but we'll get started very shortly. Remember, you can post your questions in the chat. By the way, my name is Gwen Antel. I'm a DPhil student here at Oxford, and I will be chairing your session today. We're going to get started, first of all, with Kean, who's going to tell us about late Jurassic reptiles. So I will start your presentation and kick myself out.
Hello everyone, my name is Kim and I'm going to be talking about a chapter from my master's dissertation which looked at a marine reptile fauna from Scotland. I did my master's at the University of Edinburgh and I got to work with these lovely people who I'd like to thank. I was supervised by Davide Foffa and Steve Brusatte, but I also got to work with Stig Walsh from the National Museum of Scotland and Neil Clark from the Hunterian Museum. I was also able to work with BGS and the Timespan Museum. So Helmsdale is a wee town on the northeast coast of Scotland. It's one of the few places in Scotland where you can find Jurassic-aged rocks. You might be more familiar with the Jurassic from the Isle of Skye and the Inner Hebrides, where a lot of very exciting research has been done recently. The Jurassic rocks from Helmsdale are late Jurassic in age, specifically Camarigian. And the fossils here were all found as loose boulders on the beach, and they were found by amateur fossil hunters who very kindly donated their finds to museum collections. And currently there are specimens being held at the National Museum of Scotland here in Edinburgh, the Hunterian Museum in Glasgow, BGS, the Timespan Museum in Helmsdale, and there's also a specimen at the Natural History Museum of London. So the reason that this marine reptile fauna is so interesting is because Helmsdale had an intermediate paleolatitude between the boreal and the subboreal zones in the late Jurassic. So the boreal zone had a more northern paleolatitude and includes modern-day Svalbard and Siberia, whereas the subboreal zone was more southern and includes England, the north of Germany, the north of France, North Poland, and the southern Russian platform. And because Helmsdale was in between these two zones, it can tell some really useful information about the paleobiogeographical patterns and distributions of marine reptiles. So the marine reptiles that are around in the late Jurassic oceans include the plesiosaurians, which consists of plesiosaurs and pliosaurs. Plesiosaurs essentially look like the Loch Ness Monster. They have a very long, slender neck, a small grey-style skull. They have a short tail, and so these animals were cruising specialists. They'd swim in the open oceans, and they'd feed off of cephalopods, bivalves, fish, ammonites. We've even found ichthyosaur embryos in their gut contents, which is really exciting. And then we've got the pliosaurs. So pliosaurs were ambush predators. They have a very long tail and a short neck and a large, robust skull. And these guys would eat whatever they could get their flippers on. So we found fish, plesiosaurs, other pliosaurs in their stomachs, and even a bit of a stegosaur that had unfortunately found its way into the oceans. Then we have ichthyosaurs, which I always think look a bit like a cross between a dolphin and a shark. Ichthyosaurs have a very long grey-style snout and a laterally compressed caudal fluke that would move from side to side like modern-day sharks. And the ichthyosaurs that are around in the late Jurassic include the ophthalmosauridae, which get their name from their large eyes, which were adapted to low light conditions. And then finally, we have Thaladoseuchia. These crocodilomorphs are split into Teleosauroidea and Meteorhynchidae. Teleosaurids were semi-aquatic animals. They look quite similar to modern-day gharials. These guys were covered in body armor, and they had robust teeth that would be used to pierce soft-bodied prey like cephalopods, fish, turtles, and other reptiles. Then we have the Meteorhynchids, and these guys are really weird. They're the only fully marine crocodilomorphs that we are aware of. And these guys adapted to their fully aquatic lifestyle by losing their body armor. They had hydrofoil, reduced forelimbs, and a hypocursal tail. So these were the marine reptiles that are around at this time. But who do we expect to find in Helmsdale? Well, before we ask ourselves that question, we need to work out what the environment was like. So the rocks in Helmsdale were formed in a syn-rift deep marine succession, and there are three main lithostratigraphical Cambrian aged units. We've got the Altnacool sandstone formation, the Kean boulder beds, and the Helmsdale boulder beds. So the Helmsdale boulder beds is where our specimens were found, and they were all found at Lothbeg Point, which I've circled on this map here. And the Helmsdale boulder beds were formed in a deep marine environment which had very high energy turbidity currents. And thanks to work by Nunn and Price in 2010, where they used isotopic analyses of belemnites, they worked out that the ocean temperatures during the early and mid-Cambrian were between 10.9 to 24 degrees Celsius in Helmsdale. So bearing all this in mind, we would expect to find plesiosaurs, pliosaurs, ichthyosaurs, and thalattosuchian crocodilomorphs in Helmsdale. So I went to all these, to the museums listed earlier, and I found a total of 26 specimens located at these collections. None of them are particularly spectacular, I'll be the first to admit. They're all pretty scrappy looking, and I hand examined them, I photographed them, and I also got some of them CT scanned. So 5 of these 26 specimens belong to plesiosaurs. Many of them were vertebrate, but we also have some limb and pelvic girdle elements. For instance, in figure 1, we have some paddle bones. In 1b, we've got a phalanx, which has this very typical hourglass shape, which is typical of plesiosaurs. Then in figures 2 and 4, we've got some cervical vertebrae, which have amphicheliocentrums, and they're longer than wide, which again is typical of plesiosaurs. And then we have 3 pliosaur specimens, and these are quite exciting because these are the only known pliosaur material from Scotland. We have some limb elements in figure 1, which is a humoral head. We've got jaw fragment in figure 2 and a pelvic element, an ilium in figure 3. So the jaw in figure 2 is particularly interesting. This was found by an undergraduate student at the University of St Andrews during their annual first year field trip. And it's interesting because it's relatively small compared to contemporaneous pliosaur taxa. And it's unclear what pliosaur this belongs to. I think it might be a pliosaur species. It's lacking useful diagnostic features. So we can tell that it's a pliosaur because of its robust nature. It's got circular cross-section of the roots of the teeth, which you can see in E and F in blue, and it's lacking some other features such as a dentary groove, which you would see in ichthyosaurs. There is a single preserved crown, which is the tooth in yellow. This is a replacement tooth. It possibly has a subtrihedral cross-section, but it's difficult to say if that's an artificial shape. So I can't say with any confidence what species this actually belongs to. Then we also have 4 specimens belonging to ichthyosaurs, again, mainly vertebrae and some jaw fragments. The vertebrae, as you can see, all have this typical hourglass shape in lateral view, and the jaw in figure 4, pointed with an arrow, has this dentary groove, which is diagnostic of ichthyosaurs. What's really interesting, though, is that we've not found anything from thalattosuchians, and that begs the question, why? Why weren't there thalattosuchians in Helmsdale? Was it that the habitat wasn't suitable for them to thrive in, or were they there and we just haven't found their bones yet? Well, we already know that the distribution of thalattosuchians was more restricted than that of other marine reptiles. If we refer back to this map, we can see that in areas that had a more northern paleolatitude from the boreal zone, such as Svalbard up north, there aren't any thalattosuchians there. There should be a plesiosaur up there. You've got plesiosaurs, pliosaurs, and ichthyosaurs, but no crocodilomorphs. Whereas in the more southern regions, such as continental Europe and south of England, thalattosuchians were present. So this difference in the distribution of marine reptiles might be because the thalattosuchians weren't able to regulate their body temperatures as well as other marine reptiles. Currently, we think that teleosauroids weren't endothermic. Metriorhynchids might have been endothermic, but they would have been poorly homeothermic. However, we do think that Scotland was within the upper limits of the habitable range of thalattosuchians. If we refer to this graph from Mannion et al. 2015, where they map the paleolatitudinal distributions of all marine pseudoseuchians, which are the blue dots, and marine tetrapods, which are the black dots, through time. So Helmsdale had a paleolatitude of 39 degrees Celsius, and I've circled in the red circle here the paleolatitude and the age of Helmsdale, and you can see that there are blue dots there, so we would expect to find the Latitucians in Helmsdale. So perhaps they were there and we just haven't found their bones yet. We bear in mind that the fossil record in Helmsdale isn't as fruitful as in other areas, such as the Lagerstätten in the south of England. There also aren't as many active fossil hunters in Helmsdale, so the likelihood of finding these bones is significantly reduced compared to other places in the world. And also, we now know that there were Thalattoseuchians in the Jurassic, which is very exciting. A few weeks ago, my very first paper got published at the Scottish Journal of Geology, where we described the first Thalattoseuchian material from Scotland, which was a teleosaurid from the Jurassic of Skye. So the Thalattoseuchians were up here in the Jurassic. So I think that what we've got going on is a bit of both, that we do have a sample bias at play, but that it might also have been that the conditions were simply a little bit too cold for Thalattoseuchians to really thrive here, so that there were fewer of them about in Scotland. And with these two combined, it means that we just haven't found any of their bones yet. So in conclusion, even though the fossils from Helmsdale aren't all that spectacular to look at, they're still really important and give us some really useful information about the paleobiogeographical range of Thalattoseuchians and other marine reptiles. The absence of Thalattoseuchians might be because the water was just too cold up in Scotland in the late Jurassic. But again, just because we haven't found them doesn't mean that they weren't present. And another reason why the Helmsdale material is so important is that we found the very first Scottish Palaeosaur material. So it's imperative that we keep exploring the Helmsdale boulder beds and keep finding new material. Some references. And thank you very much for your time. I'll be happy to answer any questions.
Thanks very much for that, Kim. Everybody was really excited to see that new material from Scotland, and we do have lots of people in the chat saying thanks for the chat, thanks for the talk, and we have a question here from Natalia Jagielska. Great talk. Why do you think preservation is restricted to scrappy, non-articulated material, comparing to other marine Kimmeridge deposits?
I think it's just down to the geology of the area. Helmsdale, if I compare it to other places like in the in south of England, like at Kimmeridge, where you can find things in the cliff face, like properly in situ, you don't really have that in Helmsdale. Everything is just found in the boulder. So I think it's just down to the local geology, to be perfectly honest. You also don't have as high of an erosion rate in Helmsdale than you do in other places, such as in England. So you're just not finding as much material. And yeah, I think that's just really it, is a difference in the geology.
Great, thanks for that. Do check out the chat, by the way. Lots of people showing you some love there. We have maybe 1 minute left because we did get started a bit late. What's up next? Do you have any plans for future excavations or any other sites where you'd really like to explore?
Well, I'd really like to keep exploring Helmsdale, but that's just down to time and money. I do think that the Edinburgh team are planning on spending a bit more time in Helmsdale, because there's still a lot to do there. And yeah, this material's been known for ages, but no one's really looked at it yet. So we're going to be publishing a paper on it sometime next year, hopefully. And that'll be really exciting. So yeah.
Great, thanks very much.
Thank you.
We're going to move on to our next talk now. We have Alice Maher. Can you try turning on camera and microphone? Brilliant, there you are. I will get started with your slides. And we will be hearing about the evolution of body shape, locomotion, and ecology in terrestrial vertebrates. Sounds good. Thank you, Alice. Still muted at the moment.
Brilliant. Thanks so much. So we've got quite a lot of questions.
If you go up at the top screen, do you see next to your camera icon?
Jakob says, it's a kind of two-part question. He says, does toxins or high GCMS give us more clues?
Hi Alice, best thing to do is if you can just close the window and log back in with your link, that'll reset your microphone link. While we're just waiting, just a reminder that we've got lots of talks today. The Discord server is still live where you can meet and have discussions about all weird wonderful things in paleontology. And also please do join us for the last session of the day where we have a few talks, and we will be joined by the organisers of next year's very interesting Palaeontological Association annual meeting, and also ProgPal. And I can see that Alice is back in the room. Alice, can you hear us?
Hey, I just heard you laugh. Can you say something? Can you say something, Alice? I suspect that perhaps Alice can't hear us, but we might be able to hear Alice.
We're just trying through the chat to get through to Alice, because of course it doesn't matter if she can't hear us, but we would love to hear her talk. So hopefully, bear with us one moment. We will have this sorted, because we would love to hear Alice's talk about the evolution of body shape, locomotion, and ecology in tetrapods.
We do have Alice back in the room, so just give us 1 minute. Everybody, sorry for these technical issues. We're going to move on with our next talk for now, but we are trying to get Alice back on the line, and we will do everything we can to still get that talk in this session. For now, we're going to move on to David Unwin, telling us about the rise of the naked pterosaur. Really excited for this. Yeah, take it away, David.
Thank you very much, Gwen. And I'd like to start by saying thank you to all the Pallas team, Gwen and Jack, for the marvellous work that you've been doing. And moving onwards, this talk is live from the pork pie capital of the world, and it's about pterosaurs. So the pterosaur integument has been much debated over the last 2.5 centuries. For much of the 19th century, it was thought to be reptilian in nature, perhaps scaly or maybe even glabrous and naked. Throughout most of the 20th century, it was widely thought that there was some kind of hairy covering, structures are formerly termed pycnofibers now, and that these probably covered the head, the neck, and the body, but were rather sparse. Most recently, in 2018, Yang et al. Published a paper on a beautifully preserved pterosaur from the Upper Jurassic of China, in which the integument is fantastically well preserved, and they suggested that pycnofibers were actually branched. So we ended up with the fabulous feathery fur ball, which we see on the right-hand side here. This is not just of interest to pterosaur-ophiles, such as myself. It also has much broader implications. Here we see a phylogeny of dinosaurs and pterosaurs, the Avimetatarsalidae or Ornithodira, if you wish, with time along the bottom. Prior to the Yang et al. Paper, it was widely thought that feathers arose somewhere within Dinosauria, probably sometime in the Jurassic. But if indeed branched protofeathers in pterosaurs are homologous with those in dinosaurs, it suggests that feathers themselves arose at least 80 million years earlier, possibly at the start of the Triassic, and were plesiomorphic for pterosaurs and dinosaurs, and were secondarily lost in sauropods, for example. I should point out that Campione et al. In a paper published in the Rauhut and Foth feather volume this year have challenged this particular scenario, but I'm not going to talk about that anymore today. Meanwhile, back with pterosaurs, fiber-like structures are common in the pterosaur integument. We find them fringing the jaws, in cranial crests, in wing membranes, in the foot webs, and in the tail flaps. And there's a real risk, therefore, that we might misidentify pycnofibers or even branch pycnofibers as one of these other kinds of fiber. The two could get confused. And indeed, the aim of my talk here today is to show that indeed pycnofibers and protofeathers of pterosaurs, I stress just pterosaurs, are most probably preservational artifacts, and the corollary being that the pterosaur integument was therefore glabrous or naked, to put it in more dynamic terms. We worked on a pterosaur soft tissue data set, which now totals some 150 specimens, of which we've examined about 90. Integumentary fibers of some kind are preserved in at least 92 specimens, and we've looked at about half of those. Pycnofibers form a subset of those. There are about 30 specimens, give or take, in which they've been reported so far, and we've examined and studied 20 of those specimens. Soft tissue preservation in pterosaurs is widely distributed. It's one of the great things about pterosaurs, not confined to just one clade. And we used a whole variety of analytical techniques, including right now synchrotron, which is currently underway in Germany, looking at actinofibrils in pterosaur wing membranes. So what did we find when we examined our soft tissue data set? The way I'm going to tackle this is to think about the three key areas on pterosaurs where pycnofibers / protofeathers have been reported, and that is the cranium, the neck, and the wings. And I'm going to start with the wings because that's easiest. Here we're looking at a specimen from the Santana Formation of Brazil, not Crato, as I've said here, and it's a small piece of beautifully preserved phosphatized three-dimensional wing membrane that comes from the region of the humerus. We're looking on the top surface, and as you can see, it is totally bereft of fibers of any kind whatsoever sticking out of the epidermal surface of that specimen. In fact, the skin there looks just like the skin on the backs of our hands if we ignore the hairs. But you're probably thinking, hang on, Dave, that's a very small bit of a pterosaur wing membrane. Well, there are some beautiful specimens from China discovered in recent years. Here's Fenghuangopterus from the Upper Jurassic of the Chaojishan Formation. On the left-hand side, you can see that this individual has very extensive areas of the integument preserved, including around the body and the wing membranes. They are beautifully smooth. There is no evidence of either pycnofibers or protofeathers on this specimen anywhere, really. And on the right-hand side, we see a detailed shot of part of the epidermis. In Solnhofen pterosaurs from the Solnhofen deposits, such as Rhamphorhynchus, which is one of the best known pterosaurs, we see here a beautifully preserved cast of the outer part of the wing membrane and wing finger. And as you can see, the surface of this structure is absolutely smooth. There is no external fibers whatsoever. But as we go towards the wing finger on the left-hand side, you can see there are some fibrous structures, and these are called actinofibrils. They are present throughout pterosaur wing membranes, and as far as we know, in all pterosaurs. If we look in detail at this specimen, you can see towards the bottom right there, where it says actinofibrils beneath epidermis, there's a beautifully smooth surface of the epidermis there. But up towards the wing finger, we can see that the epidermis has torn away. So we see at the edge of the epidermis exposing the actinofibrils, which are clearly therefore dermal structures underneath the epidermis, which is so thin you can actually see actinofibrils still preserved underneath the epidermis. If we go back to the 3D phosphatized Brazil specimen, here we see a TS of that particular specimen. The epidermis, as we've seen previously, is incredibly thin, and here we have a layer of actinofibrils seen in cross-section. Again, this demonstrates beyond any real question that actinofibrils are dermal structures. Towards the right-hand side, there's some suggestion that they were composite structures. And if we move lightning speed to another pterosaur, this is Sordis pilosus from the Upper Jurassic of Kazakhstan, and we have some beautifully preserved specimens with lots of nice soft tissues, including the Uropatagium, which Rachel Belbin talked about yesterday. And on the right-hand side, we can see the actinofibrils in the Uropatagium. Some of them are broken free because, as we know, the epidermis is very thin and seems to disappear quite easily. And if we come down towards the bottom right, and happily I'm not obscuring this with my head, we can actually see a single actinofibril which has begun to unravel into some very fine filaments. Typical actinofibril is about 60 to 80 microns in diameter. The filaments are about sort of 4, 5, 10 microns in diameter. And here's another specimen of Sordis where we see the wing membrane near the body. The epidermis is preserved on the right-hand side. Again, there's no evidence of an external fibrous structure on there, but we see beautifully preserved actinofibrils from within the wing membrane. And in the lower picture, what we can see is the actual normal, if whatever that might be, actinofibril on the right-hand side, about 60 to 80 microns in diameter again. And as we go towards the left, we see the actinofibrils have actually unraveled into the composite structures that they are, composed of these very fine, sort of few microns thick filaments, typically about 15 to 20 of them. The reason I'm talking about this is because if we look at the feather types, the proto-feather types identified by Yang et al. For pterosaurs, all 4 of these morphologies are easily found within the actinofibrils that we find in pterosaur wing membranes. And indeed, 3 of those proto-feather types were originally reported from the wing membranes themselves. So in our opinion, what we're actually looking at is not branched pycnofibers. We're actually looking at degrading, partially unraveled actinofibrils, which were originally helically wound. Moving on very quickly to the cranium, as you're probably well aware, lots of pterosaurs have soft tissue crests which extend upwards in all directions and are very spectacular. What we also know is, thanks to some fantastically well-preserved examples from the Craton Formation in Brazil, is that they consisted of a very thin external epidermal layer and inside a whole series of closely packed fibers. If this sounds familiar, you're absolutely right. Perhaps these are homologous with the flight membranes of pterosaurs as well. We're still working on that. The important point is that if we go to several examples of pterosaurs which have had pycnofibers reported as extending out from the top of the skull, which we see in the examples here, then our argument would be that in fact these are not really pycnofibers at all. These are remains of the fibers that originally formed cranial crests extending upwards from the tops of these skulls. And we'll focus on Gugupterus from the top right. This is from Liaoning province in China from the Lower Cretaceous. And we're going to focus in on that red box, which shows some fantastically well preserved soft tissues. What we're looking at on the left-hand side is a small piece of what was originally the cranial crest. So we see the epidermis, that continuous layer on the left, and then beneath the epidermis, we see some very well organized, closely packed fibers running dorso-ventrally, exactly as they do in that Crato specimen. And when we look in high magnification at these, we see that the fibers themselves, which again are about 40, 50 microns across, are actually made of very fine filaments, which are just a few microns in diameter. The same is also true of the neck. Several examples of pterosaurs have been reported with pycnofibers projecting from the neck, including Gugupterus, as we see here. So we're going to focus in on that patch of black soft tissue preservation by the neck. And here we go. What we see on the left-hand side here is part of the integument that originally enclosed the neck. We see epidermis, that continuous layer on the left-hand side, and that's pulled away from the underlying dermal layer of fibers on the right-hand side. And again, they're well organized, closely packed, a bit sinuous in this case. On the right-hand side, we see at high magnification that these fibers are actually composed of multiple filaments, again, a very small size, a few microns in diameter. So our conclusion at the moment is that pycnofibers reported in association with the skull and neck are in fact dermal fibers which might be homologous with the actinofibrils found in wing membranes, and that these are quite probably collagenous structures in origin. So some quick conclusions. First of all, in our opinion, branched pycnofibers or protofeathers, as they've been called in pterosaurs, we're not talking about dinosaurs here at all, are preservational artifacts. They're restricted to just one or two specimens, and it's much more likely that they represent partially decayed, unraveling actinofibrils. Dermal collagen bundles are present in the wings, and we currently call those actinofibrils. Paper upcoming on that one shortly. They're also present in cranial crests and the integument covering the neck and the body, and we think they have actually been misinterpreted in the past as external filamentous structures, which we've called pycnofibers. So that leaves us with our final conclusion, which is pterosaurs were naked. Shock, horror. I'd like to finish by saying thank you very, very much indeed to the many, many people who work in museums for providing us access to their specimens, and also to all our colleagues who've been prepared to discuss pterosaur integument at ridiculous lengths, often very late at night. And finally, I'd like to point out that the two individuals on the right-hand side didn't contribute in any way whatsoever to this project, but at least they're wearing masks. Thank you very much.
Thank you very much for that, David. Really engaging talk and spectacular specimens. We are just about out of time for questions, but there's a question in the comment in the chat, so you can respond there, or you can carry this on over to Discord. And we're now going to go back to Alice. So we're just mixing the order of these two talks. We have Alice here with us, and I will grab the slides. There we have it. Alice, can you turn on your camera and microphone? Okay, I see you. I'm not hearing you yet.
Just click on her number again. Yeah, she's turned on. Okay. Okay, go to the next speaker. I'll call her.
Okay, so we are going to go on to the next speaker and come back to Ellis again. We're going to try and make this work. We're going to keep trying. Hang with us, everybody. I'm going to switch over to Neil now. Neil Brocklehurst is here with us, and we'll grab your slides. Really excited for this. Neil's going to tell us more about reptiles, comparing reptile and synapsid diversity during the Carboniferous and early Permian. Really exciting time. So thanks for being on standby, Neil. Take it away.
Thanks. Can you hear me? I'll take that as a yes. Okay, so thank you all for coming, everyone. I want to talk today about why the late Carboniferous and early Permian may not have been as dominated by synapsids as is usually supposed. So, the amniotes, the fully terrestrial vertebrates, have long been divided into these two clades, the synapsida, the mammal line amniotes, and the reptilia, or sauropsida, the lineages that go on to produce the birds and reptiles. So what you see in this phylogeny are the lineages that diverge during the earliest diversification of the amniotes, during the late Carboniferous and early Permian. And the assignment of these various clades to synapsids and reptiles has really been pretty consistent since the 1980s. There's been movement of clades within the synapsida and reptilia, and there have been individual taxa that have been difficult to place. But on the whole, the position of these lineages within the two clades has remained relatively stable through the 1980s, 1990s, and early 2000s. In recent years, however, the boat has started to be rocked, starting with the work of Jason Pardo. Pardo analysed early tetrapods, and one of the results of his analysis was the breakup of the amphibian clade, the lepospondyles. And two lineages usually placed within the microsaurs, which are in turn usually considered lepospondyles, were drawn up into the amniotes. The recumberostrans, that's the top picture there, small critters with very compact skulls, possibly adapted for burrowing, and the Lysarophians, the bottom picture, an elongate limb-reduced clade, were both drawn into the reptiles. Next, we have the recent work of David Ford and Roger Benson. They substantially shook up early reptile phylogeny, but one of the biggest changes that they proposed was the shifting of the Varanopidae from synapsids to the reptiles. Varanopids are a group of carnivores ranging in size from 30 centimeters to more than 2 meters. They have highly recurved and serrated teeth. They've been placed within the synapsids since 1940, but Ford and Benson suggested that they were in fact reptiles. It's not all additions to the reptiles, though. This study on ear evolution by Klembara et al. Proposed a novel position for the diadectomorphs. The diadectomorphs are usually considered the outgroup to all amniotes, the sister to the amniotes. They contain things like limnoscalids, that's the top right picture, large carnivores with heavy-duty skulls, and diadectids, the bottom picture, some of the earliest herbivores in the terrestrial realm. And Klembara et al. Found the diadectomorphs to actually be within the synapsids. So obviously all these shifts of different clades between these groups are going to change our picture of the evolution of early amniotes. And what I want to talk today is about how they change our picture of species richness, of diversity within these two clades. So I want to talk about the dominance of the synapsids. The late Carboniferous and early Permian are usually described as synapsid-dominated faunas or pelycosaur-dominated faunas, as you can see in these studies, including some of my own, that the pelycosaurs, this paraphyletic grade of 6 families outside the therapsid synapsids, are considered to dominate in terms of species richness and in terms of morphological and ecological diversity. Thing is, though, there's never really been a test of the dominance of the synapsids at this time. There have been no studies comparing the diversity of synapsids and reptiles during the late Carboniferous and early Permian, either using the traditional taxonomy or the more recent revisions. So that's what I'm going to do today. So you're going to see a few of these graphs, so I'll just explain right now exactly what you're looking at. I'm looking at diversity at the more local level due to recent studies that have suggested global diversity patterns in the fossil record are probably more a signal of the spatial patterns of sampling. So each point in this graph represents a bioregion, an area of endemicity. These are defined using a method I proposed 2 years ago, where we use 2 cluster analyses, one based on geographic distances between formations, the other based on taxonomic distances, and we see which clusters are shared between the 2. So the blue points here represent the diversity of reptiles within a bioregion, the red points represent the diversity of synapsids, and the lines are the mean diversity of each within each time bin. Diversity itself is based on shareholder quorum subsampling, a method that corrects for sampling heterogeneity by drawing occurrences until you reach a particular quorum of coverage measured using Good's U. So this is the picture that we have using the traditional taxonomy. Varanopids are synapsids, and Recumberostrans, Lysarothians, and Diadectomorphs are not included. And we see a synapsid-dominated fauna for much of this time. Synapsids get off to a flying start, and they remain more diverse than reptiles throughout much of the early Permian. There are these 2 intervals where reptile diversity does poke above that of synapsids. There's this peak in the early Artinskian. I'm going to talk about that later. We'll put a pin into that for now. And then there's this crash in synapsid diversity in the latest Kungurian, while reptile diversity remains relatively consistent. This represents Olson's extinction, a minor extinction event that led to the decline of the Pelecosaurian grade synapsids, while a number of interesting reptile groups start to radiate at this time, including, for example, the Moradisaurian captorinids, large herbivorous captorinids with these impressive dental batteries. So that's the picture with the traditional taxonomy. And if we take what might be called a best case for synapsids, then we get a very similar view. So that's if we add diadectomorphs to the synapsids. If, however, we start making further changes, adding more clades to the reptiles, we start pushing the reptile diversity ever closer to that of synapsids. So this is what we have if we take all the changes that have been proposed recently. Diadectomorphs still within synapsids, but Varanopids, Lysarothians, and Recumberostrans within the reptiles. And we see that although the synapsids do get off to their flying start, during the early Permian, reptile diversity is pretty similar to that of synapsids, and the latest Kungurian drop in synapsid diversity actually pushes their diversity well below that of reptiles. And if we go for the best case for reptiles, so removing the diadectomorphs from the synapsids, we see that reptile diversity is pretty much consistent throughout the Carboniferous and early Permian with that of synapsids. Now, obviously, the taxonomic revisions are not set in stone. There's probably going to be a lot more discussion on amniote phylogeny in the coming years. So all I've really said here is that your diversity curve will depend on your chosen taxonomy. But there is something more I think can be said. You see, the formations that are included in this analysis tend to be those that heavily bias in their preservation towards larger, more robust taxa, like the Texas redbeds, the North American formations in New Mexico and Oklahoma, where we get most of our data. And large size biases towards synapsids. Synapsids pretty much have a monopoly on large size at this time. We have the giant caseids weighing up to half a ton, but still with tiny heads, and the giant macropredators like Dimetrodon. Reptiles don't really get into large sizes until the late Kungurian and the evolution of the Moradisaurian captorinids that I mentioned earlier. So is there anywhere where we can get a picture of what's happening at smaller sizes? Well, there is at Richard's Spur. Richard's Spur is a cave deposit in Oklahoma, and the karst mode of preservation appears to be favouring small, delicate taxa over the larger taxa. Richard's Spur is Artinskian in age. It is responsible for this peak in reptile diversity in the early Artinskian, and I think you can see where this is going. Richard's Spur is a reptile hotspot. By far the most abundant group we have there are Captorhinids, including hundreds of specimens of the genus Captorhinus that we see on the top picture there. There's also a noticeable diversity of parareptiles in the bottom row, including groups that are not found anywhere else in the early Permian, things like the Nycteroletarids, which don't appear elsewhere until the middle Permian. So what do we see when we compare reptile and synapsid diversity within Richard Spur? So this is again using shareholder quorum subsampling, drawing individuals until you reach a specific coverage. So along the x-axis, we have the coverage that we're drawing to, and on the y-axis, we have the number of species that you sample when you do so. At low levels of coverage, reptiles appear to be less diverse than synapsids. However, this is probably an artifact of how shareholder quorum subsampling behaves when you have a very uneven abundance distribution. I mentioned before the abundance of Captorhinus, in particular Captorhinus agouti, the most abundant specimen at most abundant species at Richard Spur. And if you have one hyperabundant taxon that is very easy to sample in subsampling analyses, then you can reach very low coverage levels just by drawing one or two species. When we go to the higher coverage levels, 0.8 and 0.9, however, we see that reptile diversity is found to be higher than that of synapsids. And this is the best case for synapsids. If we go for the best case for reptiles, reptiles overwhelmingly dominate at Richard Spur. Now, you may ask why I'm putting so much emphasis on this single locality that really has quite an aberrant fauna relative to the rest of North America at the time. The thing is, though, this aberrance is very often a feature of Lagerstätte. There was this study earlier this year by Walker et al. Comparing the taxa found in Lagerstätte to ordinary formations. And there's very little overlap between the two. Now, this isn't necessarily because Lagerstätte are from regions that have aberrant faunas. It may well be that it's because Lagerstätte tend to be modes of preservation that favour small, delicate taxa. The next thing you have to remember is that in the modern day, most animals are small. The vast majority of species are at smaller body sizes. So when we see that Lagerstätte have very different faunas to those seen outside of Lagerstätte, that isn't necessarily because they're aberrant. It may simply be that they are a window into the vast majority of the animals that were preserved at that time, but which can't be preserved in the other formations. So Lagerstätte may well be a better picture of true diversity patterns than are most other formations. At Richard Spur, the only real Lagerstätte we have in the early Permian, reptiles dominate. So to sum up, the relative diversity patterns are influenced by your chosen taxonomy, but at Richard Spur, no matter what the taxonomy, reptiles are found to dominate, and that areas of exceptional preservation like Richard Spur may better represent true diversity patterns than other formations. So it may be that the Carboniferous and early Permian were not the golden age of pelecosaurs, as has usually been supposed, but were the first age of reptiles. And I'd like to thank all these people for comments, discussion, and keeping the PBDB up to par, and of course the DFG for paying me, and thank you all for listening.
Thanks so much for that, Neil. And thanks for coming right on time. We do have time for some questions. So please, everybody, pop those into the chat. I can read them out to Neil. We have some people saying great talk. Comments are pouring in. I mean, I have questions for you, but I'm sure as soon as I ask them, then everybody else's are just going to pour in. Okay, Elsa's asking, which group was more awesome? We've got synapsids and reptiles. What's your favorite and why?
My favourite has always been synapsids because they're what I studied throughout my PhD, but I am moving more in favour of the reptiles. I really like Captorhinids with the multiple tooth rows and the sort of large size. So I think I'm on team reptile now. I've changed my allegiance.
Ooh, wow, contentious. So what's next then? Where are you looking to go with this work or follow-up stuff?
No, this is kind of a one-off side project actually, so I don't have much further to do. But anyone who to sort out amniote taxonomy, the microsaurs are probably the place to look. They have probably the biggest substantial effect on these diversity patterns, and probably more than those two clades are reptiles, I think. So yeah, microsaur taxonomy needs sorting.
All right. Well, thank you again. We're going to move on now. But if anybody has more questions for Neil, ask them in the chat over on Discord. Neil, definitely look at the chat because lots of people thanking you for your talk. We now are going to try again to get Alice on the line. Can you unmute and give us your camera, and I will pull up your slides. Great. Alice, can you try and say something on your phone? Alice, if you hear me, can you try and say something? Well, thankfully, we do have Michael Coates on the line. We're going to try for one more minute to try and get Alice. But Michael, we might move on to you. We do have Alice here in the room. I know that your audio is on. Neil, if you're still here, we're also seeing questions in the chat asking if you're on Discord. I think people want to talk to you more about your cool science over on there. Reminder, everybody, Discord server is another open platform. Think of it as our virtual coffee space.
Hello?
Hi, I can hear.
Yay!
Woohoo! Okay, so fantastic. I'm sure everybody is much anticipating Alice's talk today.
Oh, yeah.
We are going to give you the whole 15 minutes. Don't worry if we overrun because we'll just go into the break a little bit. Session number 12 will still start on time. Just, Alice, tell me when you want me to advance your slides and I will move them for you, okay?
Okay, brilliant. Thank you.
So happy to have you here. Take it away, Alice.
Thank you. So, hi, everyone. Sorry about all the technical difficulties there. I don't know what's going on, but my name is Alice Maher, and I'm looking at the evolution of body shape, locomotion, and ecology in tetrapods. So, next slide, please. Thanks. So we know that body shape plays a universal and fundamental role in the mechanical and physiological function of all organisms. And because different environments and behaviours place different demands on the functional mechanics and physiologies of organisms, it's expected that body shape should vary adaptively across animals occupying different ecological niches, which may also be constrained by other factors, notably body size, phylogenetic history, and the ecological trajectory of evolutionary change. Given the logical and universal potential for natural selection to act upon body shape, many studies have sought to investigate associations between body proportions and ecological niche occupation. While these studies have regularly identified important adaptive trends in body shape evolution, they've tended to focus on individual taxonomic or ecological groups and on a specific or individual aspect of body shape. However, wider availability of imaging approaches that allow 3D quantification of whole organism shape and phylogenetic comparative methods now allows explicit consideration of the role of multiple confounding factors like body size and phylogenetic history into statistical analysis of whole body shape change. To our knowledge, no study to date has systematically investigated patterns of whole body shape change across tetrapods using modern phylogenetic comparative approaches. Next slide, please. So we had 3 main aims for this research. However, we found so many amazing results and so many significant results that I wouldn't be able to go through them all in this presentation with you. So we're mainly focusing on some of the interesting things that came out of aim 2 and 3. And that was, how has locomotor ecology shaped the evolution of tetrapod body shape, and how has trophic ecology shaped the evolution of tetrapod body shape. Next, please. So how we went about doing this. In figure A, you can see that we created a data set of 410 tetrapod species spanning all major orders, clades, and most families to be as diverse as possible. These species also range from the Permian all the way to the Quaternary today. In figure B and C, we can see that each species was assigned to a locomotor and a trophic category. And to address the aims, we extract not only linear measurements of body segment size from our 3D skeletal models, but also use mathematical shape fitting to generate 3D volumetric representations of body proportions. This allows us to examine changes in body segments whose overall size and shapes are poorly captured by linear measurements, and also provides a whole organism measure of overall body size against which to normalize body segment dimensions and assess allometric changes in proportions. Next, please. So looking at the first aim, how has trophic ecology shaped the evolution of tetrapod body shape? So figure B shows that negative allometry in skull volume was recovered for all trophic groups, but is least marked in carnivores, which scale closest to isometry, while herbivores scale with greatest negative allometry. Greater selective pressure to maintain relative head size in carnivores likely relates to hypercarnivory and large prey specialization. A larger skull size gives these species a relatively bigger gape and stronger bite force with which to subdue large struggling prey, and greater ability to subsequently reduce food mass. Figure A shows a snapshot of the carnivora and artiodactyla tree and clearly shows a relationship between larger skull sizes in carnivores that you can see at the bottom and smaller skull sizes in herbivores that you can see up near the top. Next, please. So the relative allometric signal observed in head size between carnivores and herbivores is, however, reversed in the neck. In figure D, we can see that carnivores exhibit negative allometry in the neck and isometry relative to head size, and are statistically different to herbivores, whose necks scale with positive allometry relative to overall body size and negative allometry to head size. Necks increase the feeding envelope and total range of motion accessible to the head-neck system, which may be beneficial to herbivores but undesirable for carnivores, where the more inherent structural stability of a shorter neck is beneficial to prey capture. Figure C shows this is exemplified in non-avian dinosaurs. The relatively largest necks and smallest heads are found in herbivorous sauropod dinosaurs, while carnivorous pteropod dinosaurs have relatively short necks and large heads for their body size relative to many terrestrial vertebrates. Collectively, a relatively larger torso and neck and smaller skull in herbivores suggest selection towards food processing shifting from the mouth to the gut, particularly in mega herbivores like sauropod dinosaurs. Next, please. So for our analysis of the evolution of locomotor ecology and body proportions, we focus on the limbs, which are primarily responsible for powering different types of locomotion. The evolution of flight appears to have had the most significant and wide-scale effects on body proportions in tetrapods. Active flyers and soarers show significantly larger humerite, forearm, and metacarpal segments, and overall forelimb lengths to almost all other locomotor categories. Manus lengths are also larger on average in flying taxa, but not statistically significant. Flying groups also show the strongest positive allometry in proximal forelimb segments, and are significantly different to most other groups in this respect. These trends most likely relate to a greater evolutionary pressure for a large surface area to volume ratio within the wing to increase wing area and muscle mass in flying birds. In figure C, we can see that forelimb elongation in the dinosaurian ancestors of birds appears to have been initiated in dromaeosaurs, see a Microraptor and Velociraptor, with the earliest taxa hypothesized to have had modest powered flight capabilities, showing similar forelimb segment sizes to extant flying birds in our data. Distal limb segments are not statistically longer in flying taxa, and this could be indicative of greater ecological specialization. The largest manus segments within flying taxa are found in the Chiroptera or bats, which evolved longer forelimbs through the elongation of the forearm and manus rather than the humerus as in birds. The manus in bats needs to be highly modified for climbing and hanging off walls of caves, whereas the hindlimb shows comparatively little specialization. Next slide, please. So within the aves, however, hindlimb specialization does occur. For example, the largest metatarsal and pes lengths are found in species that spend a lot of time on land, for example, the flamingo and the ostrich. In figure E and F, in addition to flight, the evolution of locomotion in bird-line theropods was also marked by systematic change in the relative lengths of hind limb bones, which is hypothesized to be mechanistically linked to walking and running mechanics. Basal theropods had a long humor relative to distal limb segments, particularly the metatarsal segment, and are thought to have powered the stride from the hip. Along the lineage leading to birds, the fossil record demonstrates a reversal in the relative length of limb bones, with the femur making up a relatively small proportion of limb length and the metatarsal segment greatly enlarged. This is suggested to be causatively linked to a shift in joint power away from the hip in favour of the knee and ankle joints, as observed in extant birds. Our new data sheds light on how limb segments here change relative to overall body size during the evolutionary transition. And data suggests that femoral length did decrease in certain derived clades of non-avian theropod dinosaurs like the dromaeosaurs and transitional taxa such as Archaeopteryx, and remained relatively reduced in specific extant avian subclades. However, our data suggests that a reversal occurred in early avian evolution, and that the relative size of the femur seen in basal theropods is equalled in many extant avian groups, including flying taxa. Next slide, please. So another interesting result we found was amongst bipeds and quadrupeds, and particularly regarding dinosaurs. So hind limb segments and overall hind limb length are longer in bipedal striders, but the segment volumes are on average larger in quadrupeds, probably due to more robust limb bones for weight support. The evolution of quadrupediality from a bipedal ancestral state is very rare in tetrapod evolutionary history, but did occur on 4 independent occasions, 3 times within ornithischia and once within sauropods, which you can see from the stars on the screen. Our data highlights how quadrupediality impacted dinosaur body proportions and the differential changes that occurred in independent quadrupedal lineages. The shift in forelimb use to active locomotory support is not universally associated with its elongation relative to overall body size across quadrupedal dinosaurs. Indeed, most ornithischian lineages remain stable in relative forelimb length or suffered a relative reduction, which is particularly extreme in the armoured thyreophorans. Partly as a result of these trends and due to stronger negative velometry and hind limb length within sauropods, these groups also exhibit very different ratios of hind limb to forelimb length, with relatively equal lengths in ornithischians, but a clear progressive trend towards relatively longer forelimbs and hind limbs in sauropod evolution, which may be linked to neck enlargement in sauropods and a cranial shift in centre of mass position also. Next slide, please. We also recover previously unrecognised disparity in relative trunk size across quadrupedal dinosaurs. While all quadrupedal lineages appear to have evolved slightly enlarged torsos for their size, we find relatively small increases in ceratopsians and hadrosaurids, moderate increases in sauropods, and much larger increases in armoured thyreophorans, such as the ankylosaur that you can see at the bottom of the screen. Together with the changes in limb proportions, this suggests complex and varied selective pressures behind the evolution of quadrupedal locomotion across dinosaurs. For example, torso enlargement in quadrupedal dinosaurs may be closely linked with increasing gut size and megaherbivory across dinosaurs generally. The most extreme investment in relative torso size is seen in armoured thyreophorans, which also evolved reduced forelimbs, and together these traits are likely to have negatively impacted on locomotor performance. It's possible that dermal armour evolved in concert with these changes to provide active or passive predator defence, given an investment in torso size above locomotor performance. In contrast, the hadrosaurids, which lacked any dermal or cranial ornamentation, retain more cursorial limb proportions, overall limb size, and a smaller torso, and presumably were therefore more superior in locomotor performance to outrun predators. This study has demonstrated that multivariate approaches, which consider multiple segment lengths in combination rather than individually, are required to statistically separate bipeds from quadrupeds. Next slide, please. So in conclusion, so we had 3 conclusions for the 3 aims. Again, we've only focused mainly on the bottom 2, but feel free to email me or ask me any questions later about any of the other results we found. But we recovered differences between locomotor and dietary groups, which highlight key adaptations in body proportions that mechanistically underlie the exploitation of major ecological niches, as well as revealing patterns of change across major macroevolutionary events. And our results emphasise the pivotal role of body proportions in the broad-scale ecological diversification of tetrapods. Next slide, please. So I'd like to thank my supervisors, Karl, Phil Cox and Tom Maddox. I'd like to thank everyone at the Institute and everybody involved that's helped with this paper. I do apologise for any technical difficulties that has also happened as well. It's very odd because the microphone was working, but hopefully you've got the presentation from this and understand what I was trying to say. So thank you very much as well to Pallas for organising this.
Thank you so much for that. I think I speak for everybody in the chat in saying that was worth the wait.
Oh, good.
And if anybody has questions, please do pop those into the chat. I know it takes a minute for them to appear. We do have time for questions.
Brilliant.
While I wait for other people's questions to come up, just on your conclusion slide, you had a couple there that you didn't really have much time to talk about. Would you like to tell us more about how these body proportions might influence the broad-scale ecological diversification of tetrapods?
Well, I think one of the key things that a lot of researchers focused on is within certain families, so carnivores, as I mentioned before, artiodactyl. Nobody has seemed to have really compared it just as a whole. So how does this shape affect animals as a whole across time and throughout evolution? So we found, yeah, so many interesting comparative anatomy, so many interesting statistical results. So yeah, I mean, you'd have to, it's such a broad question and such a broad research that you'd probably have to go to exactly what you would want me to look at for you. So which part of the body and which shape that you're thinking of?
Yeah, well, if anybody has a favorite body part, post it in the chat and you can, I'm sure Alice would be happy to tell you about it.
Happy to.
Great. As if you can see the chat, definitely look at it. Lots of people just saying fantastic talk, great talk, awesome talk. People really found this interesting.
Oh, thank you very much.
We are going to move on for now to our last speaker. So I will pull up the slides. The other sessions will still be running on time, but we will have this one session before the break. So we have Michael Coates as our final speaker today. Can you turn on video and audio?
I believe I'm on.
I can hear you. You don't have to be there on video, but if you would like to be on video, you could turn that on.
I'm looking for the video bit. I should be on. Where's the video button? Help.
So at the top of the screen, you should see 4 little circles. Yep. And next to the mic, there should be one that kind of looks like a stopwatch. That's a video.
Okay, we're here. Good morning.
Brilliant.
Yeah, well, I plead innocence. It's early here.
I'll give you 15 minutes and I will kick myself out. Thanks so much.
Okay, right. Well, I will try and steam through this quickly and not eat into your coffee time. Anyway, yeah, so thanks to the presenters. Great meeting so far. And this is an opportunity to present yet another talk about missing data and mashing matrices together. So this is a collective effort, and these are all the wonderful team behind it, and particular thanks to Ben Otu for dragging me back into the wonderful swamp of early tetrapods, and Vish, who kicked me into saying, look, we ought to put an abstract in. So in it went, and here we are. So this project comes out in response to numerous publications and a ton of new data on early tetrapods that's appeared over the past decade or more. New tools, big projects such as the Tweed project up in the Scottish borders have generated a lot of this. But the problem is, or at least the issue that came up to us in our meetings, etc., is that there's no existing phylogenetic analysis that covers all of the data. The state of the state of play in this area has got to the almost absurd level where there are more early tetrapods known, or would be early tetrapods, let it put it that way, than equivalent actinopts. So we're talking about the interval of the Devonian through to the lowest Carboniferous. And this unusual ratio is something never to be repeated later in the record, really. Here, trees. You've seen some of these already. Neil Brocklehurst showed the Pardo et al. One. Phylogenies from recent high-profile publications, notably include those from Pardo et al., Alberg and Clack, Besnasov and colleagues. Importantly, these character sets are populated, and in some instances absolutely mostly populated, with data drawn from the skull and especially from the lower jaw. Here's one I prepared earlier for all you Blue Peter fans. But the point is, there's plenty of other data that you can pull characters from, and these are being underexploited, things like isolated humeri, girdles, limbs, etc. They're morphologically disparate and rich in character data. And on top of that, there are some notable absentees from the taxon sets. In particular, the Devonian tetrapod Tulurpeton, the third man of the late Fomenian, headless wonder of uncertain identity from European Russia. Tulurpeton has been included in matrices, largely analyses run by Marcello Ruta, but these are the exception that prove the rule. And it's also been popping up in some pretty strange places. By the way, in all of these diagrams, we see the red arrow that denotes the node for the tetrapod crown group. And even in the most recent tree of early tetrapods, in a detailed analysis of humerus shape and inferred adaptation across adaptive landscapes, etc., Tulurpeton's missing, and we've got a host of mystery objects in there called Watcheriids. So, one final point. Note, in this one, the tetrapod crown node has been moved back into the Devonian. So, these discoveries and phylogenies lead us to the question of what do they tell us about the much discussed Romer's gap, this data void in the Tournasian. Is this gap now filled, or at least populated with tetrapods? Is Romer's gap a thing of the past? It was ever thus. And in this analysis too, or in these analyses, the origin of crowned tetrapods as a Devonian phenomenon, what does that tell us about the tetrapods that ought to be turning up within the Tournasian? Where are the Tournasian amniotes and stem groupless amphibians? Right, so the project has some basic aims, and these are combined matrices. We want to take a maximalist approach to fossil inclusion and explore the signal and the implications of these data. We want to date the crown node. Are they sufficient, the new data, to plunge it into the Devonian? We want to check survivorship from the End-Devonian into Romer's gap. We want to survey the kinds of tetrapods present by the End-Devonian. How do these new Devonian limb tetrapods compare with Mississippian forms? And we want to test for the effects of incompleteness. Are these fragments informative or noisy shrapnel flying around wrecking the tree? How do these new data change the fish tetrapod scenario, the transition? And how do these fossils align with the trackway data? So this is our taxon set, so you can memorize this. Yeah, it's a lot of taxa. The main point is that we haven't rejected anything because of insufficient coverage. What about the character sources? Well, jaws. Plenty of data in jaws, and indeed jaws have driven character sets rather a lot recently. Limbs. I've thrown up a selection of fossils here just to point out some of the clustered similarities. I hope you can see in some of the boxes, above my balding head and off to the side there, the strange kidney-shaped huneri put together, the standard L-shaped things often said to be embolomeres. And up above me, there's a bunch of shoulder-girdle Clythra. And these are from very different parts of the globe, Siberia and Southern Africa and so forth, suggesting we might have incipient groups in here. Okay, this is the new beast on the block. This is brand new work from Ben Otu, and I'm pleased to say it's not revised and pending. it is accepted. So it'll be appearing in Zooge Linsop early next year, one hopes. And it's his work on the postcranium of Wacheria. So this is the first full reconstruction of the postcranium of Wacheria. So we've got a whole block of new data to chuck into the mix. So this is our character matrix. So what we've got, 60 taxa, 151 characters, multi-state, etc. And we tried to rebalance cranial and postcranial. The data sets that we've mined for data and pulled in include the ones on the list there. It's noticeable some of them have just been moved, and entire sort of portmanteau of the things from larger data set to larger data set. And we've seasoned these with a lot of new characters, etc. Now, the key stat in here is the appalling level of incompleteness, barely achieving 36% completeness in terms of characters scored per taxon, which is pretty shoddy. So we lined them up, and we got this sort of miserably hollow curve of taxa, this basic histogram of completeness. You can see there's a great long tail of taxa which are less than 20% complete. As a simple visual check on how these distribute through time, here they are, the histogram color-coded to match the bog standard colors from the geological column. And you can see it's a mixed distribution. I mean, after all, some of our earliest taxa, we're running from the Franian through to the Tournasian, include things like Eusthenopteron, Tiktaalik, and now Opistostigi, which are pretty completely known. So it's not as if the earliest ones are barely understood. It's a pretty awful mix all the way through. And if we block this out into sort of big chunky histograms, sort of Franian, Furmanian, Tournasian, you can see the green blocks is average completeness. The Visayan out-achieves the whole of the rest. The underachieving block in there is the Tournasian. So if Romer's Gap is now populated, it's barely populated. It's still, in terms of data, Romer's trough. So another way of looking at these data, here's the matrix artfully arranged to show that basically we've got blocks. We've got blocks almost of mutually exclusive data. We've got a load of limb data up there in blue. We've got jaw data in green there. And we've got a few taxa you can see in the middle, which are kind of stringing these things together. So let's run the analysis. And oh, fantastic. Look what we've got. Some miserable rake that's turned up there. Surprise, surprise. Not much point in running a Bremer analysis or decay analyses or bootstraps on something as hideous as that. But if we look at an Adams consensus, and I know all the problems associated with Adams, spurious groups that can pop up, etc. Nevertheless, there's the hint that we've got incipient signal in there. So the next thing we tried was to run partition tests and have a look at jaw data and limb data. And the result from that is that there is signal. And the signal from these two data partitions is pretty consistent. So what we've got there is a kind of agreement subtree figured on the side. Signal strength and consistency, we might expect signal strength to improve if we start excluding a lot of the tail. And indeed, that's what happens. You see strict consensus. Now, what we decided to do was to put a measure on signal strength, which is basically ratio of nodes to terminal taxa that we get in consensus trees. And if we do that, we can see that at the end of our miserable data set there, we've got a score of 0.08. But by the time we've excluded taxa of roughly 20% more or more missing data, only 20% preserved. They've got you got the point. You can see what's going on there. We're up to sort of on the way to 0.9, so we're getting a pretty well resolved tree. So we might expect to get a nice, neat result like this. With there's a blue curve represents taxon completeness, and we've got Adams and strict consensus converging pretty much, while we've got taxa that are just about 25% complete, but there we're getting pretty resolved trees and pretty much the same nodes in both. But in fact, misery, it's not anywhere near as good as that. When we look at the actual result, we can see that the curve is one of peaks and troughs and plateaus. And this might be expected, given that a taxon that's only perhaps 30% complete may consist of no more than a collection of plesiomorphes. So we recognize that this procedure is one of only many possible routes through a data set like this. We haven't yet succeeded in managing to get to run the stability test on this, but it will be part of the project when we get to completion. But one more question that came up with this is, if we track through these curves and these peaks and troughs, do the nodes stay the same? It's all very well looking at signal strength, but are we looking at the same trees? So we went hopping from peak to peak here. And in fact, this is what we find, that the nodes are pretty much staying the same. We do have conservation of the underlying signal. So if we look at the fully resolved tree marked in red there, all the nodes in that appear in our 60 taxon data set at the far end. And we can see in the middle, there's a 29 taxon tree in the middle with, I think it's about 13 new nodes in there. It's 11 of those persist through to the end tree. So our argument from this is that there is signal in this data set, and the signal is consistent, even though it's attenuated, as we add increasingly incomplete taxa. So here's our big reveal, our grand result, a simple time calibrated tree, which places the tetrapod crown node at minimum date within the Visaean. And if we look at the raw number of taxa in the middle to late Fomenian, it's about 13, but the implied lineages crossing the boundary add an additional 20. So this implies that we've got an awful lot of survivors from the Fomenian running into the Tournasian. It suggests that the Tournasian cast of tetrapods is effectively a Fomenian holdover, that all these groups originated earlier. The initial radiation of limbed tetrapods, therefore, proceeded before the end Devonian extinction and were there ready to populate Romer's gap. Now, back of envelope estimate of evolutionary rates along the spine of the tree estimates it comes out at roughly double the evolutionary rate that's going on in, what's going on in the Fomenian is double the background rate, and the rates plummet in the Tournasian before recovering within the Visaean, some 15 million years after the Hangenberg. But before we get excited about these radical results, fragments, errors, inserti, cedus, and homoplazy, could we be utterly wrong? We've acknowledged that many of these taxa are no more than fragments. And several of these taxa that are forcing the dates are known from really minimal amounts of data. These could have dropped to artifactually low insertion points on the tree because of incompleteness, taphonomic ratchet, nod to Rob Sansom here, and others might have hopped in the opposite direction, driven by homoplazy or questionable character score decisions with limited extra data to shield the spurious signal. The net effect of both kinds of error is to add branch length to the tree and push nodes deeper into the strat column. So we've got the data set, we've got the results, we've got the taxa ranked. We can use a sliding threshold on this to prune taxa off the end and yield the results straight away. So if we move it merely to exclude all those taxa known less than 5% of character scores, we get quite a different tree shape. The effect's dramatic. We have many fewer boundary crossing lineages. Branching events along the backbone are more evenly distributed through the record. Turnover is evident at the Hangenberg event, but there's no suggestion of rate change. And so here the Tournasian tetrapods appear as results of post-Devonian branching events. There's a modest Romer's gap radiation. Irrespective of the alternative taxon lists and tree results, our conservative estimate of the fin to limb transition zone lies between Acanthostega and the branching event giving rise to Elgin-Erpeton. In these results, our conservative estimate places the fin to limb transition just above the Valentia Island trackways, but this still remains some 10 million years short of the fabled Polish trackway. So what about the thing we put in the abstract about pushing these limbed tetrapods into the Gavetian? How did we get to that? Well, it's another fragment effect. A possible vomer, palatal bone, is known from the same lowermost Franian locality as the jaw fragment named Livoniana, And if we sorry, I'm getting a hint to shut up and go away, I suspect. If we...
20 seconds left to wrap up, and then we are going to have to give people a little bit of a break before the next session, which is...
Okay, right, you get the idea. Cram these things together, they hop up to the limb tetrapods. That's what forces the things back to the base. So there we are. And we have Britignathus, teamed up. It's a Watcheriid from the Devonian. So the key thing I want to say at the end of this, you had it all. Thanks to everyone, and particular thanks to John Bolt and Jenny Clack for many arguments and wry humour.
Thank you very much for that talk. And we do have some questions, so you can answer those in the chat or respond to people over Discord.
I will look in the
questions
chat.
there. Just an announcement for everybody. We realize that this session is way over time. So is the parallel session. We're going to start session 12, which starts at 12 noon, 5 minutes late. So you're welcome to join that session now. You'll be able to get in the room. But talks will start on a 5-minute delay. So the first 5-minute speed talk will start at 12:05. Also remember, tonight is the Paleovision Fossil Contest, so do join in for that. It will start at 7:30 UK and Ireland time, and that will be streaming here from the Oxford University Museum, and it's going to be a fantastic event. So do join in for that, and we'll hope to see you in later sessions today as well. So thank you all for coming. Thank you all for your patience with our technical difficulties. Have a nice quick break, and we'll see you later.